Now, before I get started, I'd like to acknowledge kind of the team actually that did most of the work. So Yuri Lysogorsky, Mateusz Moravec, Anton Bochkarev, Minam, Matteo, Yan, and Eslam. So their work I will present. And I should also say that I was very happy to see at this workshop and at other workshops at the long program presentations that are very much related to what I'm trying to show here. So in the afternoon, Michele Giaiotti certainly, and then I will heavily build on Jan Janssens and Jörg Neugebauer's talk on Pyron for workflow management. And there were talks by Gabor, James, Boris, Ivan, Christoph Aden already. And so actually I'm a little worried if I can tell you anything new here, but let's see. You decide at the end of this talk. Now, as the title said, what we want to do, and I think what we all kind of want to do, is we want to start from some fundamental theory. The fundamental theory is the many electron Schrödinger equation, and we want to end up with the prediction of properties of materials. And in reality, of course, it's typically not possible to do this, and so we use an approximation density functional theory as our starting point. And that's a very, very solid starting point for many materials. But still, we cannot just jump from DFT to properties of materials. So say we want to predict a phase diagram. Then if you look at how phase diagrams are computed, typically you need a few thousand atoms in a box. You need to shake them a little bit with molecular dynamics or Monte Carlo simulations. So you end up with 10 to the 12 atomic force calls in total, typically for a free energy computation, and that's just too expensive for DFT, or only if you have millions and millions of CPU hours, you can use them. And therefore, the typical approach to go from density functional theory to the prediction, let's say, of a phase diagram, is to use some intermediate models, in particular interatomic potentials, and then you do molecular dynamics or Monte Carlo simulation to go to properties of materials. Now, and at each of these steps, so this is kind of a workflow already, and at each of these steps, multiple decisions need to be taken. You have to decide which exchange correlation functional, which basis you use, so LCA or plane wave basis, K-mesh density. For the potential, it's the same, which type of potential, a classical potential or machine learning potential, is charge transfer relevant or not? What kind of the simulation, is it a thermodynamic simulation for a phase diagram, or are you in after some transport? And so this all needs to be managed, and it's something, of course, that you would like to do relatively quickly, ideally. So if you go back a few years in time and the development of classical potentials typically is or was an art, and then an expert would sit there for a year and come up with the best parameters for a certain problem. And of course, we would like to be able to go from DFT to properties of materials within a few days, ideally. And the main limitation actually is setting up the DFT reference data, but if you have access to sufficiently large computational resources, then this is possible. And also, of course, in order to be able to do this smoothly from fundamentals to the properties of materials, it is absolutely critical to have a homogeneous workflow, to have a workflow that is robust and reliable and reproducible. And so, as I said already here, I build on the talks that Jörg Neugebauer and Jan Janssen give on Pyron as a Pyron for workflow management. And then I can focus on density functional theory to interatomic potentials. That will be actually the main part of this talk. And afterwards, I'll show some properties of materials. Now, if you go from DFT to interatomic potentials, you typically don't do this in one step, but this already is a workflow. So you take your DFT and you bring it together with some reference structures. There's already choices that need to be made here. Typically, people use kind of reference structures that they collect from some databases. But then if you look at work from Danny Paris, for example, he tries to come up with more clever ways, or he came up with more clever ways of sampling reference structures based on entropy maximization. So you take these reference structures, let's say tens of thousands, put them in high throughput DFT calculations and generate a database. And of course, also this part of the workflow needs to be robust. Then once you have your database, this is what you use for training. So you bring it together with the potential of your choice, train your potential, and then afterwards you have to see that you test it and validate it. And then depending if your potential is good enough in the tests or not, you may want to improve your reference structures, you may improve your training data set, for example, with the help of active learning, or you take your potential in the simulations that you want to do. And I'd like in this presentation take you through some of the steps of this workflow. So I just assume that this part here, from DFT reference structures, high throughput calculations to a database, is more or less set, and then start here with the training of the potential. So given a certain potential, how can we train it? How can we validate it? How can we make sure it's a good potential, or improve it if necessary, and then use it for simulations? And the very first part here is the potential itself. So as I said initially, there's a choice that one has to make. Do you want to use a classical potential? Will it be sufficient for the task? Do you prefer to use a machine learning potential? And clearly, we make our specific choice here. We use what is called the atomic cluster expansion. And I very briefly like to, or in the next few minutes, like to introduce the basics of the atomic cluster expansion. So the idea underlying all interatomic potentials is that the system that you describe is local. So the interactions are local. There may be long-range charge-charge interactions, but you handle them separately. Okay, so you can sit on one atom, and then you can define a cutoff radius, and this atom only interacts with other atoms that are within this cutoff sphere. And then you need a way to compute the energy of this atom. And if you're interested in the energy of the system, it's just the sum over all the atomic energies. So the focus is therefore on the prediction of atomic energies. How can we compute energies per atom and the energy of this atom I in its environment? This is the task. And if one would do this in a kind of naive, direct way, then one could say, okay, I write down the energy as a decomposition of pair contributions, plus 3-body contributions, plus 4-body contributions, 5-body contributions, and so on and so forth. Now assume that you have, let's say, a closed packed material like FCC, and then you may have 100 atoms in the neighbor list. And the effort just related to doing this is then just scales like with the order of this n-body terms. Okay, so if you have 100 neighbors, then you will have 100 pair terms. But if you look at the combinations with 3-body terms, then you have 100 directions where each of these pairs can point to. So 100 times 100 is 10,000. For 4-body, then it's 100 to the power of 3 to the power of 4. And so this means if you need millions of operations just to compute the energy per atom, then that will not be computationally feasible. So that will not be a fast potential. So we have to come up with something else. And what Jörg Behler did, and that really started the field of machine learning into atomic potentials, he said, well, maybe we can get away with 2-body or 3-body contributions. So he said, okay, I have descriptors that depend on pairs and descriptors that depend on 3-body contributions. And I compute many of these descriptors. And I use descriptors as an input layer to a high-dimensional neural network. And I ask the neural network to predict the energy per atom. And what then comes out is that the neural network is of course, a very nonlinear function for these descriptors, and that the neural network implicitly manages to recover higher body correlations. Okay, so then the input is only 2-body and 3-body, but the output essentially of the neural network contains implicitly 4-body, 5-body, n-body interactions in this energy. And so there's an accurate prediction of the energy per atom. what we would like to do with the atomic cluster expansion, we would like to go back to this decomposition in pairs, 2-body, 3-body, 4-body contributions. And we would like to understand, can we do this explicitly? And so the approach is the following. We sit on our atom here in its environment, and the environment is characterized by neighboring atoms. So each atom I has its neighbors, I, neighbor 1, neighbor 2, so we have all these vectors. We call this the configuration of atom I, and we know somehow the energy of atom I must be determined by all these vectors here. And the question is now how? And to this end, we formally introduce a basis and an inner product before we can put in a basis. So the inner product is just the usual inner product, and once we have the inner product, we can put in basis functions that are orthonormal and complete. And that's pretty much like in electronic structure calculations. When you think of a Hartree-Fock approximation, for example, you start with single particle basis functions. Okay, so we now have single bond basis functions. We have basis functions that only depend on this bond and on this bond and on this bond. And we just ask them to be orthonormal and complete. And then we take products. In the next step, we take products of these basis functions. So these are 3 pairwise basis functions multiplied together into cluster basis functions. And it's very easy to show that these cluster basis functions are then also orthonormal and complete, which means if we just take enough of these cluster basis functions, we can cast the energy of atom I in a linear combination of these cluster basis functions. Okay, this is expansion coefficients times cluster basis functions, and formally, because everything is linear, we can even project out these expansion coefficients. And as I said, this looks very much like a Hartree-Fock approximation, and then a linear combination of Slater determinants to improve the basis function. Only that we're lucky here because our atoms are, of course, invariant under permutation. Okay, what the energy, if we exchange 2 atoms of the same species, we want that the energy doesn't change, so we have a symmetric function as opposed to a fermionic system that is much harder, where one has to take care, of course, of the antisymmetry. And that's essentially all for the atomic cluster expansion. That's the idea, that we have basis functions in a complete basis in the local atomic environment. Now we still have to take all these products, and one may argue that to evaluate these products is cumbersome and expensive, right? So we have these products and we have to sum them over all neighbors. And with the exact same argument that I just made, this is computationally very expensive. So if each of these atoms has to sum over 100 neighbors, then we get 100 to the power of 4 operations that we need to do. Luckily, if you just look at this, what this is, it can just be rewritten like a sum to the power of 4, right? And this just means we can rearrange these products in such a way that they are very efficient to evaluate. Namely, irrespective of the order of the expansion, they scale linear with the number of neighbors. And this means we can do high body orders very efficiently, 5-body, 6-body, 7-body orders. So I just show this in a more illustrative way maybe once more. So we start with pairwise 3-body, 4-body, 5-body terms, where we have a very poor scaling with the number of neighbors. So n to the power of 5 with the number of neighbors, which means that wouldn't be an interatomic potential, would be far too slow. Then we just reorder we exchange multiplication and summation, and we get product terms, essentially a polynomial, and this is what we call here atomic base, that is linear with the number of neighbors. Therefore, it's fast to evaluate. And as Christoph Ordner has shown, it's not only fast to evaluate because it's linear, but also because it can be evaluated recursively, and every single multiplication gives you a new basis function. So it's really efficient up to high accuracy and high body order. Okay, so this is the basics of the atomic cluster expansion. We're not completely done yet. Yesterday we also heard about symmetry in in kernels. And here the same, of course, from an interatomic potential, one expects that it's rotationally invariant, for example, or that it's invariant under inversion. And we didn't put any of this information in there. So far, it was just a complete expansion without any consideration of symmetry. Now, if something is invariant under rotation, it makes good sense to work with the rotation group, and basis functions for the rotation group are the spherical harmonics. So this single bond basis function that I introduced earlier, we represent them as radial functions times spherical harmonics. And for the spherical harmonics, we then get products of these. We get these cluster basis functions that are products of these single bond basis functions. For the products of the spherical harmonics, we know how to reduce them. Okay, so this is just like spin coupling. So you have spherical harmonics with angular momentum L1 and another with L2. You multiply them together, you get a resulting angular momentum L that is defined with, or can be computed with, or the possible ways how this can couple is computed from Clebsch-Gordon coefficients simply. And if you have higher order couplings, 5 spherical harmonics, then you get just generalized Clebsch-Gordon coefficients, which themselves are just products of Clebsch-Gordon coefficients. And in this way, we can start from our cluster basis functions, and then with the help of generalized Clebsch-Gordon coefficients, filter out all the angular momentum couplings that do not lead to something that is rotationally invariant. Because after all, at the end, we are interested only in the part that is rotationally invariant. So we throw out everything that is not rotationally invariant for a potential. And these are then basis functions for the space of local atomic environments under the constraint that they need to be rotationally invariant. So we can rewrite the expansion in terms of these basis functions. Now, if you're not interested in a potential, in something that is rotationally invariant, but you're interested, for example, in a vector, then the only thing that you need to do is you need to slightly modify the coupling of the Clebsch-Gordon coefficients here to couple to L equal to 1 for vector or L equal to 2 for tensors, say. Okay, so this expansion immediately is applicable also to vectorial or tensorial properties. And now, because the ACE expansion is a complete basis, of course, we can look through the literature, look at other descriptors that have been used, and can represent them in the form of the atomic cluster expansion. In particular, I'd like to highlight here. One here is the moment tensor potential, because the moment tensor potential is also a complete basis in space. It's just formulated in a slightly different way. And one can make kind of, if one likes, a one-to-one mapping from the moment tensor potentials to the atomic cluster expansion or back. So we now we're at a stage where we have a complete basis that spans the space of atomic environments, and we can take linear combinations of this basis expansion. So we can take it like this. But we don't have to do only one of these expansions, but for every atom we could take several of them. And so we could write the energy as some kind of nonlinear function that depends on several of this, what we call atomic properties. So the physics behind that, or the chemical intuition, maybe, okay, we have a bonding contribution, and then we have a repulsive contribution if we think in terms of a simple tight binding model, and the repulsive contribution may be short-ranged or something like this. Okay, and so this means we have a degree of freedom that we can still play with, and we ask this degree of freedom F to be scale invariant and to be not dependent on chemistry or basis functions. And one very simple way to realize this is a linear term and a square root term. And why are we choosing this? Typically, we don't have to, but it's kind of our favorite choice. Well, if we reduce our expansion only to pair contributions, then we have pair terms here, and then we recover essentially the Finnis-Sinclair potential or the embedded atom method potentials, or kind of this basic classical potentials that are very well established since the 1980s. And then when we make the expansion more complex, then we say we expand this systematically to include 3-body, 4-body, n-body contributions.
What are the upper scripts 1 and 2?
So this just means these are 2 different expansions. And these are the same basis functions. So the expensive part is to evaluate the basis functions, 3-body, 4-body, the relative expensive part. And then this product here is cheap. And so we just have two different vectors here to multiply them. And so these are optimization parameters. And as I said, one could, for example, if one would like to reproduce a tight binding model, one could fit the repulsive part first, and then one could fit the bonding part to have this kind of transparent physical approach, for example. Okay. Good. So then the next part, if we decide we run with the atomic cluster expansion here, we of course have to train it, and the training itself contains workflows, and I just have the workflow that we go through.
Someone has a question.
Yeah, just a quick question. Coming back to the potential, we had the potential from Jörg Behler where he had like very simple descriptors and a very complex model mapping the descriptor to the relative energies.
Yeah.
You in some way are on the opposite side. You have very extensive descriptors, but very simple model mapping those descriptors. Can we benefit by, for example, putting the ACE descriptors into a neural network?
Absolutely right. So this form here is so general. If you like, you can write immediately Jörg Behler's neural network. Right? It comprises this, and I fully agree. There's I mean, we like this one because it's simple and has some physics or some chemistry inside. But probably the optimum is somewhere by taking a few more of these and making F slightly more complex. So there's an optimum between, I think, the approach that Jörg Behler took and the pure linear expansion somewhere, I think. Yeah. Okay. So then we go to training. So we have as input for training atomic configurations, and we want to attach to the atomic configurations energies. And these energies, of course, depend on the distances, so on all the atomic positions, but also on trainable parameters. And to train, we write a loss function where we compare the energy of a structure to a DFT reference energy and the forces on each atom to the DFT reference. And one could extend this to stresses, of course, if one like, and so on and so forth. And so then we have to minimize this loss function with respect to the trainable parameters. And the trainable parameters are essentially two groups that we have here. First, we have to optimize our radial function to get kind of a minimal LCAO basis. And second, we have the actual the actual expansion coefficients from the ACE expansion. So we just run through that, compute the energy, compute the loss function, and then minimize this. And this is a nonlinear optimization problem that we have implemented in TensorFlow in a code called Pacemaker that is available on GitHub if you're interested in playing with that. And typically we have a few hundred or a few thousand optimization parameters, and the optimization takes, let's say, 1 or 2 days depending on the GPUs that you have available. We have speeded that up recently a little bit so that we get down to hours with the next portion. And because we have a basis expansion, and not only because we have a basis expansion, but as we have a basis expansion, we can order our basis functions hierarchically, right? So if you have a plane wave basis, it's natural to order the basis functions according to their wavelengths of frequency, right? And you have a plane wave cutoff. And we can do the same. We just order our basis functions by the body order, and then by the radial order, and by the angular momentum order. And so we can get to a one-dimensional ordering of our basis functions, and then we feed successively more basis functions into the fit. So we get more basis functions here, and of course, the more basis functions we have, the smaller the error gets, and we get a nice algebraic decay, and that's how typically the fit proceeds. And at some point, of course, if there's either there's noise in the data or we miss some physics, charge transfer, or whatever, then this will saturate, right? But typically, we always get this algebraic decay, so we can really converge the expansion with the number of basis functions.
Question?
Yeah.
So the linear ACE line here, I'm confused about the error that you're reporting on your
Yes.
slope lines versus the flat linear ACE
Yeah.
line.
So these are taken from publications as just this is what these publications have found as a constant. If you look at publications, they typically give one error. They won't give you the error as a function of the number of elements. So this is just the value taken, and this was from Gabor Chani's group, where a linear ACE was fitted to the same training set for ethanol, and they found this. And but we have fitted here, if I may go back a few slides, this nonlinear term, and this just gives us. Actually, we looked at this. How much does this nonlinear term give us? It gives us we need about 10 times less parameters to achieve the same accuracy as the linear ACE. So right, physics, starting from physical insight helps. Just it essentially, you start here at few parameters, you start lower and then go down. And that's, yeah.
What does train single feature?
Yes, so exactly, very good. So this is a relatively small data set. So we have the training, and then we have 10% or so, as we typically do it, set aside for testing. And you can see that the test slope is not as steep as the train slope, and this just signals immediately that your data is insufficient. But we just run with this data set. And then for the test slope, we get a slope of 0.5 in this log-log plot. And for the train here, 0.75, and the slope of 0.5 is typically, I think, what one would expect. So that's roughly where we want to be.
So is the linear ACE, is the correct comparison the blue points to the linear ACE or the
No,
brown
actually this one. So actually it should be this one, the test one.
So then isn't that your additional term here is not able to get as good as?
Oh yeah. Sorry. Yes, we're able to get as good there. It's just this is just meant to show the decay, well, the systematic decay. But yes, absolutely. This continues. It's really it's not the idea to show how good we can be. It's roughly the spectrum here. Yeah. Yes, please.
So I'm very curious about the basis function order. You said there's three things which control that, right?
Yeah.
How do you sort them? Because they all, there may not be just one order of them, which gives you that strictly monotonic decay.
Absolutely,
right?
yes. There are as many orders as you can count. It's not like with a plane wave where it's very simple that you order
That's
it.
easy, right? Yeah,
Exactly. But one can write, so the products of angular momenta one can order according to sum of L's, so L contributions. And then we just say the radial part we order in the same way, and then how we order the body order is more empirical.
But how do you order the combination of them? If you change those
So a sum of n radial contributions, sum of L contributions, and sum of body order. And I should say there's not one way we have to ordering it.
Okay.
But there are several related ways, and they eventually all end up very similar.
I get it.
So there's some stability.
There's not a unique way, but there's a sensible choice,
exactly,
and it works.
Absolutely.
I like it.
Absolutely. Yeah.
Thank you.
Yeah. Yes, please.
This is lots of questions on this plot. So what's the rough number of parameters over data points? That ratio, what would that be for these sort of, I'm getting to 2,000 functions per element?
I don't know actually at the moment how many data points we had for this, but typically we make sure we have many more data points. So typically the data sets that I'll show later a little on have, let's say, 1 million or 2 million atomic environments, and we may have 10,000 training parameters. So that's roughly, so just to be on the safe side. Yes.
So is there an easy way to identify if I need more radial terms or more angular? Is fitting the potential, I feel this is a bit challenging to say, okay, in which direction do I now increase my parameter space? Do I make the model more complex?
Yes. I think there's no real easy way, right? It's like also with the DFT LCAO basis, are angular contributions more important or are more radial functions more important? It's something that you want to try. It's system dependent also, I think.
You can do a hydrogen atom, right? So for each n you have L-1, right? Something like that.
Well, absolutely. That is more, I think, right. The SNAP philosophy is in a way a bit like this. Of course, one could do it exactly in this way. We don't do it and say we just keep it as a parameter and then have this this kind of empirical or sensible way of ordering the basis functions that will implicitly take care of this, right? It will tell you, okay, now you added enough radial functions, now it's time to add another angular contribution and so on and so forth. But there's no kind of ground truth.
So when you train these, do you have these parameters to balance between the radial and angular functions? Is it your hyperparameters that you want to?
So we do this more or less empirically in combinations that we found that work well. So we did exactly the tests typically, or I use a few radial functions, I use more angular contributions, or the other way around. And of course that can be made more systematic, where's the optimum. But so far it seems to work just reasonably well, right? There's probably room for improvement, but not terribly much, I think. Yes.
Wouldn't one be able to see directly from this type of convergence curve so good
Absolutely.
the ordering is? Or because if I get a plateau and then it jumped down, so I know I did some...
Absolutely. Yes. For example, if you would add only pairwise functions, then at some point they wouldn't help you because they couldn't lower the error anymore. Absolutely. And the reason that we not seeing this here means we seem to do something right. So let's put it like this.
So, principally, if you would look at the first derivative and you are seeing so that you have kind of monotonous behavior, that's the best ordering you can get.
Yes, I think so, yes. Absolutely. Yeah.
On a log scale.
On log, yeah.
On a log, yes, absolutely. Okay, so then just to show where do we get, Jan, I think, showed this graph yesterday, but without the contributions from ACE, and so right there are a few machine learning potentials. There's the moment tensor potential. As I said, the moment tensor potential one can map if one likes exactly on ACE, so that's related and similar to ACE, and then there's the question how one can faster evaluate the basis function, essentially based on spherical harmonics or moment tensors. Okay, but at least we seem to be competitive here. And the next thing I would like to address very briefly is chemical complexity. Right now we have worked this out for the space of local atomic environments. But what happens now if we say we want to do multi-component alloys with high entropy alloys with 5 components? And of course you just can count the number of different occupations that you can have for such a 5-body cluster. It's just 5 to the 5 as compared to a single element. So this means formally if you want to parameterize this, you need about 3,000 times more effort or more reference data to parameterize this in an exhaustive way than for a single element. And of course that's a showstopper for 10 component alloys, and for technical alloys, of course, that's where we want to be. For super alloys, for steels, all these things, they have many components. Luckily, we can use here tensor decomposition. So this is the expansion coefficient for this, let's say, for a 4-body cluster here. And it's symmetric, right, with respect to indices. Nothing may happen, so one can decompose this nicely into a tensor and then gets a very much reduced representation, which allows us to immediately fit multi-element systems. So that's an example of a fit with a 33 element from a 33 element data set. And then there's just a nonlinear dimensionality reduction, and I'm just showing the 2 first dimensions here. And what this gives you, you kind of recover the periodic table from the data, because you immediately see that elements that are close by in the periodic table end up also close by on this graph. So we're kind of learning the chemistry of the 38 elements just from the DFT data and end up with sensible ordering. Sorry? So this is just you can do the same graph with a simple PCA analysis. It looks similar, slightly different, but this is just a nonlinear way to reduce dimensionality and to find out what are the two dominant contributions in the dimensionality, and they are just plotted here.
So it means you can get your rank 5 tensor into a rank 2 tensor?
Yes.
So,
But
and
many-
all the others, so essentially here you can stop already at rank 2
Yes.
for the tensor decomposition.
Yes, one can, and this holds for any higher body order, so absolutely one. The only thing where one has to fit the whole thing, then our rank 2 tensors, but one doesn't need, here one only has one, and here one has many, right? That's the price that one has to pay. One gets a new axis, but that's just tensor decomposition of symmetric tensors. One can always do that, and then that seems to be efficient in chemical space. So that seems to work very well. It's something that we're doing at the moment. Yes, please.
Did you just say that on the next slide that you just need 2 coordinates to describe all these elements and how your coefficients change for these elements?
No.
This is just the 2 components that are plotted.
Exactly.
There are way more in there.
That's just the dimensionality.
How many do I actually use? How many?
But the tensors are rank 2. So that's Jörg's point. That's absolutely right. But here, right, this is a much higher dimensional space, but we're only showing the 2 dimensions that come out to be most important in this nonlinear analysis. And they're different. If you use different dimensionality reduction methods, then that looks slightly different. But you always get this connectivity of similar elements. So the chemistry is somehow recovered. Okay.
By how much are they the dominant components? Like, I mean, do you have a really well-defined break in your component distributions?
I don't. I can only say very loosely because I don't know now that the first few components are really the most important ones, and then there are many that are in the sum important. So, but I can't say much more now. I would have to look at the data. Yes.
So do you understand the topology of this graph? Because I'm really confused. It doesn't look really like I would expect like a periodic table, or because oxygen is here, carbon is here, you have then these lines, so I would expect more something like clustering, or so that I'm seeing
because
more.
it's a nonlinear.
It's it's nonlinear, and B, of course, you get what is in the data, and the data set biases somehow. It's not the whole possibility of the periodic table, but I think it still gets some elements that should be close together that end up being close together. So there seems to be something behind it. So or in other words, for me at least, the tensor decomposition seems to work because the different elements are related. They have related chemistry, and so we can group them closer together. That's essentially how this is working. Yes, please.
So if I understand, these are the most important descriptors, right?
Yeah.
So if you take a 3-dimensional descriptor, is this very far from, or would this look similar, or how important is the third one, so to say, right?
Yeah, that was yeah. So I can't say quantitatively. I mean, the first few ones, the first 10 or 15 ones certainly are all important, and then there come many 100 that all have small contributions, so you cannot ignore them. Right? So we looked at when can we ignore some of them completely, and because typically one wants to get to accurate representations, even if you cut somewhere and seem to cut out only a small part, that can result in significant errors on this scale. So that's. Yeah.
Can you see how good is now? Let's say is this fit, so that we get a feeling so far. You can something like 10 millieV.
I don't have numbers, but it's something that's typically what you have. Yeah. Sorry, I just didn't bring the numbers, so I don't know. Yeah.
So there's many hundred little parameters. How sensitive are they to numerical precision of the input data? I think it's an old question, but it's still.
Yes. So this is right. This goes back to the training. How robust is the training here? And I mean, there are all kind of different strategies to make this robust. But a very simple strategy is to add a few weights here. And one thing that we typically do when we say we're not interested in very high energy structures, let's say for typical applications. And then we give these high energy structures less weight, and in this way, we just balance the reference data a little bit. That adding new data doesn't distort the current fit completely. But that's all I can say, right? Because as we don't filter the data specifically, one could do this, but we just typically work with the data that we have. And of course, if you change your reference data, your fit will also slightly change. The question is how much it changes, and our experience is it's reasonably robust.
But what I mean is you have 12 digits of numerical precision if you calculate something exactly double precision and everything always. And so if you cut off digits beyond the 12 digits, you have a certain noise that enters your
Absolutely.
But if you had, say, 2 or 3 digits for some reason, what would happen?
So for example, right, this is all on GPUs, and we experimented in the beginning a little bit with single precision and not double precision, and then that doesn't work. It's not good enough for the optimization. So one needs some significance. Okay. So then the next part is, okay, now we assume we have the atomic cluster expansion as a potential, we trained it, now we need to test it and validate it. And actually we had, with Jörg Neugebauer and Jörg Behler and Carsten Albe, a collaboration exactly on validation of potentials in Germany, where we said there are 3 different types of validation that we want to do. First, we want to compare to the raw DFT data. So that's just the force mismatch and the energy mismatch. Then we want to be sure that we can predict something that is reasonable if we compare it to DFT. That's level 2. And the third thing is of course, at some point we can't run DFT reference calculations, so we have to compare to experiment, essentially. And one example that I just show here is on the fly validation. So when we run our pacemaker optimization code, these are the numerical iterations, then you can slot in properties that you like to monitor. And so, for example, that's copper. The stacking fault energies are important for copper, and they are then computed at every few iteration steps, and you see if you're converging to them. And the dashed lines here are the DFT reference data, and we see we are converging, but we're not converging perfectly, which is also not unexpected, because our training is only on energies and forces, and defects are always differences between large energies of the perfect bulk and then the distorted bulk. So this is not fitted explicitly. So this is kind of already halfway a prediction. But this is then just what we get, and we kind of have to be happy with that, or kind of put in more structures that sample this explicitly. Another typical test, of course, are phonons. So phonons are immediately spot on, and we just compare them with other potentials here again for copper. Where it's getting a bit more tricky is if you just put your system in a 2D layer. So you just take copper, which is normally obviously not 2-dimensional in vacuum, and you just ask yourself what are the phonons there. And if you look at the kind of simpler potentials, they predict negative or instability here, whereas ACE correctly predicts in accordance with DFT that even in 2-dimensional copper, the phonons are stable.
Do you compare with the existing potentials, for example, SNAP? Is it something you take from the literature?
Yes. So right, it is. So this in this sense, so we take our ACE, where we did not put in this structure explicitly, but we put in some small clusters. These other potentials, of course, have been trained independently of us from other reference data. And this does not say that if you would take SNAP and train it with the same reference data, that you could also not get this right. So right, it's just an observation at this stage. Then, of course, binaries are of interest, and this is just the platinum-rhodium as a function of composition. We see the change in the lattice constant, and you see the gap between the kind of the PBE reference data and the experiment is kind of the largest already. And here the convex hull we get, so the energies are 25 electron volt, and typically you see we get 2 to 3 25 milli-electron volts, we get 2 to 3 milli-electron volts. It's not perfect, but that's just what we get like this. Okay, now we have validated this, and I see I'm coming to the end already with this. So the next step is then, is this good enough, or are we missing something? And we use active learning based on d-optimality. If we have a small if we have some data set that spans some space here, and if we enter new data that increases this space, then we take this into account in our training. That's the idea for the optimality. So you just see, for example, for carbon molybdenum, how this active learning generation fill the space. So that's again a nonlinear dimensionality reduction here. Or we do small clusters, platinum, rhodium, where we initially have larger extrapolation grades, and now we do, after retraining, after active learning, we reduce the extrapolation grade. And this, yes?
What was the surrogate model in
No, we don't have a surrogate model. We have these are our basis functions. So this is just a two-dimensional example, but we have a few hundred basis functions, and they span the space that we're interested in. And for the optimality, that's all we need. And so then we can do this also in kind of when we do simulations, let's say with a few thousand atoms, we monitor this extrapolation grade. We find one atom that has a large extrapolation grade, we cut it out and pad it, put it into DFT, add it back to our reference data. And so one can therefore just run on the fly, and whenever there's something coming up that is uncertain, one can put it into training and update the potential. Okay, so I rushed through that briefly because I want to show you some of the work that we're actually doing. That was only the workflow to get there. And before that, one last thing is, of course, we want to do simulations where, as I said, where we compute phase diagrams, for example. And we heavily rely on LAMs for doing that, so molecular dynamics or Monte Carlo simulations in LAMs. But then we combine it in workflows for non-equilibrium thermodynamic integration, where we ramp up from one reference potential to the potential of interest and down and compute the free energy. And in this way, for example, we can compute the free energy of the phase diagram of magnesium, right? So this is the phase diagram of magnesium, pressure versus temperature, obtained from PBE data fit from FHI AIMS. So we have done high throughput, a few 10,000 calculations, then fitted it, then put it into our free energy computation, and then end up with the phase diagram. And if I may, there were so many. I just continue a little bit, and then you stop me, because I just have a few slides. So carbon, for example, we do in the same way. So we just do DFT calculations, then we parameterize it, and then we see what happens. And so this is just these are a few structures here, some relevant for carbon, some not so relevant, as a function of nearest neighbor distance. And then with the ACE, you can see the circles are the DFT reference data. We fit that smoothly. If you look at other potentials that are out there, typically the developers did not take into account large volume data in fitting, and therefore you see this kind of wiggly behavior for larger volumes. And then we can just we can also compare the CPU time, of course. And as I said, ACE is efficient compared to other methods. So gap here is here. The turbo gap, they did an excellent job bringing this down 10 times. And we are here, and if we put it on GPUs, we are reaching, let's say, the 1 microsecond per atom force call on a complete GPU timescale. And with this, we can then just do simulations through atoms in a box, and this is just a quench simulation at different volumes. And yellow is four-fold coordinated diamond. If you have a larger volume, you form more open graphite structures. So you see graphite layers forming here, and you here see just more fluffy graphite layers. Or we can take the same potential and break it. And of course, nothing happens there. It's just a brittle crack. So one should assume nothing happens, because if you compare it to other potentials that are out there, if you do the same numerical experiment, you see graphitization at the crack tip. But that's not a problem of the potential. That's a problem of the DFT reference training data. So in the gap 20, the reference training data that they used for diamond had a much higher energy than graphene or graphite, whereas the functional that we use here, it's just PBE plus D2 correction, is in between. And so therefore, the diamond lattice has a high energy, and the system forms graphite whenever it can. So it has nothing to do with the potential, but more with the parameterization reference data. We can take graphene. We saw that yesterday, graphene in the electron microscope. Now we can just pull at it and look at the defect structures that we can find. Or we can just put carbon atoms in a box at high temperature with a little bit of argon and see what happens. And we form all these fullerenes then. And we can look at how they react to fullerenes and so on and so forth. And if I'm
we've taken a lot of questions during
okay, good.
this.
So I
think you're allowed
otherwise you stop me. Then we start to look at nanoclusters, right? That's for catalysis. And actually, one thing I should point out here, Ovito is of course very, very important for us. So much of all of the visualization that we do is with Ovito. So it's all these little movies that I'm showing you. And so then if you build such a nanocluster and you put platinum in the core, you see quickly it goes to the surface. And I'm sorry for changing the colors here. So if you have 30% platinum, 70% rhodium cluster, then immediately the whole surface is covered with platinum, whereas the core remains rhodium. And if you mix in more platinum, then that seems to form a solid solution in here. Now that's very clear in the simulations, but if you look at experimental databases and you look at the surface energies of platinum and rhodium, they are very similar. If you look at the PBE predicted surface energies, platinum surface energy is much lower than rhodium, and that drives the segregation. So this means what we can very well predict the DFT reference data, but it doesn't mean that what we predict here is really what should happen in reality. So we're really reaching the predictive capability of the PBE functional immediately. And that actually, if you do this experimentally, so these are experiments from Tina Scheu's group and at the Max Planck Institute for Eisenforschung in Düsseldorf, you see that this rhodium core, so this is the experiment here, remains stable and even at higher temperature, where we predict thermodynamically it should dissolve here. But if we do a molecular dynamics simulation at 1000 Kelvin for 2 nanoseconds, nothing happens. So at least the solution process is very, very slow. Or we can look at silver palladiums, just put a little droplet on the surface, look at the equilibrium structure, and so on and so forth. So I can go, if the chairman allows me to go on, I'll go on until tomorrow morning. But
perhaps not.
Okay. No, but a little bit. I can continue a little bit. So another thing that we started to look at is water, and it's really right. We have our whole machinery. I said this whole workflow. So it's really one can just start the DFT calculations and do this, and then one gets water. So the water molecules are just moving at room temperature. And we need only 300, with active learning, only about 300 DFT calculations to get this going, right? So supercells with about 300 DFT calculations. And we have recently also done this with MP2 reference data, and then, of course, MP2 with path integral, and we can compare all of this. So what is the difference between the ref PBE D3 normal DFT functional and the MP2 reference data, where the MP2 data was taken only from clusters because there wasn't any periodic data available. Yeah.
Actually, for these kind of molecules, do you also use like 5-body interactions, or where do you cut the cluster expansion?
Yeah, absolutely. We use typically 5-body, up to 5-body, but only a few 5-body interactions. There's no clear rule. Typically 5 to 6-body interaction. Yeah, and then we can I don't know, look at fullerene in water. We can put water in a little tube and see confinement effects. We can just play. We can look at the melting of water, right? So this is just the liquid front moves into the solid. In this way, we can determine the melting temperature of water. Or, but I'll really stop. Then we can just look at molten salts. We can we can even without any charge transfer, we can just run them. We can look at transformations in ferroelectric materials, and we can, and that's the last thing that I show, we can extend this whole formalism to include other variables, magnetism, and then we can look at the magnetic transition in iron, for example. So if we ramp up temperature, we now have a system that has atomic degrees of freedom, and every atom carries a magnetic moment that can rotate and that it can change its magnitude. We have ferromagnetic here, all aligned in parallel, and at high temperature, they point in all kind of random directions. And so we are paramagnetic. But the important thing is the prediction is in agreement with the experiment, the magnetic moment do not collapse. Right? It's a really paramagnetic state that is predicted. Okay, so I think I'll just skip over the rest and conclude. So I wanted to show you that we have a robust workflow from DFT to properties of materials. We can do this in days. And if you want to see how this is done in practice, we did actually a hands-on workshop, and where not only the ACE was fitted, but neural network potentials and EAM potentials were all fitted in Pyron. And you may want to just look at this tutorial if you're interested. Thank you very much.